All right. Ready? Don't know. Oh well. Probably because we're streaming it online.
There's only 2 people watching it. I wanted on his name.
That's true. Yeah, I could see it. Yeah, it's it happens. It happens.
Where's Zoe at? I should jump.
All right, so this is where we left off. And before I forget, I did. So remember, we're going to be using Pairwise Permutational T-Test as our post hoc test. And also, under the quizzes and exam, I uploaded the xmisslights.csv file. So you can have it. The plans for Welch's ANOVA. So what I suggest doing is getting your R ready, import the data, load your libraries, and then go through and answer the questions. It's only about 6 or 7 questions, but I give you 20 minutes to do it, and that should be more than enough time. Right? This is where we left off. So we ran our permutational ANOVA. We have the script, and remember there's only really 3 lines that you adjust. These 3. And then you run the chunk, and you get the p-value. It outputs the p-value. Once we output the p-value, all right, then we have our write-up. So based on the p-value, we do have a difference in survival. How do we report it? So oftentimes I would say permutational ANOVA of 10,000 iterations revealed that survival differed by color, and report the p-value. I didn't report the F statistic. You could, if someone asks. And where do we find that? Pops up right here in the environment window. That's where it pops up. And if you needed it, or you know you're going to need it, then it doesn't hurt just to go ahead, instead of relying on remembering to pull the value off of the global environment, you just at the bottom type in fobs, and when that gets run with the chunk, it'll report both the p-value and the f observed value. So you can do for like a scientific paper, I would state the permutational ANOVA was being run and state how many iterations in the actual method section. And then when I'd report it, I would just say survival differed by color, and my test was permutational ANOVA, and I report the p-value at that point. Since I already said in the methods how many iterations were run, yeah, I wouldn't repeat it. So we know a difference exists. All right? We know a difference exists, so what's next? Post hoc test. This will be permutational post hoc test. And really, what we're going to be running here is pairwise permutational T-Test. Or you can run pairwise permutational ANOVAs. We'll get the same p-values. All right, we'll get the same p-values. So why did we run the permutational ANOVA to begin with? Why did we run it? So usually we're going to run it because we violated our assumptions. So if our assumptions of ANOVA were violated, then we also violated the assumptions of our post hoc test. Now, that's not entirely correct. There are some post hoc tests that we can run that account for unequal variances, other than a pairwise Welch's T-test. There's a Steele's multiple comparison procedure that counts as a non-parametric multiple comparison test that we could run. There's a Gaines and Howell test that we could run. There are options, but I think as more and more research has gone into these randomization tests, we're realizing that the randomization tests, not only are they easy to do on a computer and fast, but they're actually pretty good. Possibly better than some of the other conventional tests that we would have run. All right, so if we violated ANOVA and are going down this permutational ANOVA route, then it stands to reckon that we probably need to continue the permutational path. All right. Thus, so if we violated ANOVA, then we also violated the assumptions of the post hoc test. Thus, our options for post hoc tests, our option is singular for a post hoc test is pairwise permutational T-tests, or ANOVA, with p-value adjustments. All right. That's going to be our option. This adds time and it's tedious. It's going to be tedious. So we're going to introduce permutational T-tests. All right. This will work even if we just had two samples and wanted to run a permutational two-sample T-test. So we didn't address what do we do if we only have two groups and we violated normality. Well, we can still run permutational ANOVA, or we could run a permutational T-test. All right, so this question, the question that is answered with a permutational T-test is, are the means equal? The means of two groups equal. So our null hypothesis is that the means are equal, and the alternate is that the means are different. And there's really no other post hoc test that we need to chase. Because if we know that they're not equal, then we just look at the values, we look at the means, and conclude that one is larger than the other. All right, our test statistic that we use is the T. But we could use the difference in means. All right, we're going to use it, I believe we're using T. Yep, we're going to use our T. Difference in mean and using the T will come up with the same p-value. You'll get the same conclusions. So our degrees of freedom, none. And again, why is that? Yeah, we're making our own null distribution, which in this case would be the equivalent to a T. Now, if all of our assumptions are met of it, if all of our assumptions of a T-test are met, then our test statistic T will follow a T distribution with the appropriate degrees of freedom. But if we violate any of those assumptions of a T-test, then our test statistic will not follow that T distribution. It's the same idea as the ANOVA. Reporting, we need to do our conclusion, interpretation. We have to give our the test that we ran, number of iterations, and it'll likely be the same as for the ANOVA. and then p-value. Test statistic is optional. You don't necessarily have to report it, just like the ANOVA. If someone asks you for it, you can always give it. But again, I wouldn't report the difference of means if I was using that as a randomization test. The R code, we will use a script. All right, and this is where our pairwise permutational T-test come into play. So that's posted. I'm going to copy it and paste it. All right. So once you get this, we will kind of work through it. I'm going to just fix this just briefly. Just make it just a bit cleaner for consistency. So, yeah, spelled. All right. So the first thing we're going to do is create our subset. So this is if we have a data set where we have more than two groups. So we're going to create a subset and call it subdata. That new data set will only have two groups in it. So to create that data set, or that subset, we have to give it the data frame that we're working with, and then we have to specify our grouping variable. And this grouping variable should be that X that we will be replacing. All right? It's going to be those X's. So then from the subset data, we're going to specify our dependent variable and our independent variable. So our dependent variable will be the subset of data frame that we're working with, and then our dependent variable, that's our Y, and then our grouping variable X's, which we use that variable name up here. So replace data frame in line 1 with your data frame. I'll put data frame in quotation marks. All right. So replace your data frame in line 1 with your data frame. Number 2, replace the y in line 2 with your dependent variable. So whatever that variable is. Now in the ANOVA we use data $ variable name. We don't need to do that. I've already done that with the subdata. We just have to give it the variable name. All right, we just have to give it the variable name at that point. We already have the data $. And then we're going to replace the X's in lines 1 and 3 with your independent variable. It's your grouping variable. And then replace condition 1 and condition 2 with 2 different levels, found in your independent variable. And we're going to do this for every combination. That's what we're going to be replacing in the script. The process is going to be the oh, hold on, and our iteration. I guess the number 5. Missed that. Replace n with a number of iterations, usually 10,000. 10,000. All right. So here's the process for this. We will subset our data frame to get a new one with only 2 groups. That's what we're going to do. So we're going to subset our data frame to get a new one with only 2 groups. So once we have that, then we will extract the independent and dependent variables and save them as a new variable. Just like we did for the ANOVA. We're going to pull out the independent variable, call that indvar. We're going to pull out the dependent variable and call it depvar. Then what we're going to do is specify the number of iterations and then fourth we will run a t-test and extract and save the test statistic. And for that, that will be our t-obs. So just like the f-obs, we're going to use t-obs to make our comparison to our null distribution so that we can calculate a p-value. Then we will create an empty vector that will hold our randomized test statistics. And this is trand. This vector will be our null distribution. Then we will generate the null distribution. By assuming no difference in means. So this is the loop. Now why I had this. Now my tab only gives 2 spaces instead of 5. That's crazy. All right, so in the loop, what we are going to do is shuffle the independent variable. And this is sample without replacement. And when we shuffle, we basically eliminate any groups, any grouping that's naturally in our data. We break it apart. So I should say, our assumption of this, just like with all randomization tests, is that we have random and independent data. And that's it. So we're going to shuffle the independent variable. That's our grouping variable. We're going to sample with replacement. And then we will run a t-test against our randomized group and save the test statistic in trand. So that is our loop. So rvar, that is sampling of our independent variable, that's shuffling of our group. And then we're going to run our t-test and save the test statistic t. Once we have that, and once the loop is run, I guess we have C. Repeat A and B until we reach n iterations. So we're just going to repeat it. Then our last thing is calculate the p-value, which is the proportion of t-rand values that equal or exceed t observed. And we have the same thing. We might not actually get our actual t observed value during a randomization method, but it is a valid test statistic that we could have gotten. We just need to run even more randomizations. So we include that value as part of our null distribution because we actually saw it. So that's why in our p-value calculation we add a 1 to the numerator and add a 1 to the denominator. Both of these represent our observed test statistic. Note, we save the absolute values. And so we have saved the absolute value of our test statistic. This is both our t-obs and t-rand values. Why? Why might we do that? What does a t-distribution look like? So we didn't do this for the f distribution, for A nova. We just took the f statistic. Why did we use just a regular f statistic, but we used the absolute value of the t statistic for this one?
I would say it can't be negative.
Okay, so f can't be negative. So A nova, the 1 versus 2 tail didn't apply, right? Because we're at a certain value and f is just going to keep getting larger and larger. So our proportion getting a value as extreme or more extreme could easily be worked with just using the traditional f value. But when we look at the t, our t is centered at 0. So we can have a negative value, we can have a positive value, right? That was when we used our pt function. You had to specify lower dot tail equals t or lower dot tail equals false. All right, and that was based on do we have a negative or do we have a positive value? Our p-value is as extreme or more extreme. If we're in the positive, we're above, which works for this p-value calculation. It's the sum of t-rand greater than or equal to t observed. That works if we're in positive. But if our t observed and t-rand is negative, we would have to flip this to less than or equals to. But that idea goes back to our alternate hypotheses. So if we specify that one mean is larger than the other and want to run a one-tailed test, we do have to keep track of if we're working with the positive or the negative t's. But since we don't care which direction it is, it's either are they equal or are they not equal, we're looking at a two-tailed test. So what we can do is take that entire negative half of the distribution and flip it to a positive, which means we've got both the negative and the positive on one side, and thus this equation now works as a two-tailed test. Interesting? So, why overall? The t-distribution is centered at 0. So we have both positive and negative values. Our HA specifies a two-tailed test. So our p-value is the proportion of t observed, or I'll say proportion of t null greater than t observed, right, and the proportion of T null less than, I should say less than or equal to, T null greater than or equal to T observed, and T null less than or equal to the negative of T observed. I'll add some spaces too. This is why we did 2 times PT, because it's symmetric. That's why we also did 2 times P null. And since I added spaces, I'm going to add parentheses too to help clarify. All right. Is a proportion of T null that's greater than, we'll say the positive T null that's greater than or equal to the positive T observed, and the negative T null that's less than or equal to the negative T observed. If we take the absolute value of T observed and the absolute value of T rand, then we only need to look at the proportion of T rand greater than or equal to T observed to get our p-value. So we're doing it more as an ease of script writing, that we don't have to kind of mess around with the script. We don't know if one was larger or smaller. We didn't know that going in. That's why we did an ANOVA or permutational ANOVA. So if we didn't have any a priori knowledge that one was larger than the other, then we don't have that knowledge going into our permutational t-test. So we're inherently running a two-tailed test every time we run one of these permutational t-tests. All right? So that's our script. We've got a couple more places to replace, but I think it's going to be okay. So let's go back to our example. Example, this is flowers.csv, flower.csv, I guess. All right. So we know the difference in survive exists between the colors. Which colors differ? So first, let's determine the colors. Let's determine the levels in colors. Because we need to know the exact name of the level to use in our pairwise permutational t-test. So how do we do this? What function did this? Levels. Yep. So I'm going to use levels, flower, color. All right, so we've got blue, green, red, and white. All right. And I'm going to look at the means. Oops. 2. Because what I'm going to do is go from smallest to largest, start comparing the means from smallest to largest, just to try to make it a little bit easier for our comparisons. So I'm going to use the aggregate function. We are doing survive as a function of color, and maybe we've already done this, but I'm going to do it again in preparation for my pairwise permutational t-test. So survive is a function of color, date equals flower, our fun is mean, and we also get the color. So what we're going to do is look at, we have white, green, blue, and red. That's the order I'm going to make my comparison in. So let's run each permutational t-test and save the p-value. So now I'm going to go back up to my script and go ahead and copy it. I'm only going to do it one time for now. going to start making my substitutions. So this is my flower data set. Our grouping variable is color. So that is going to replace all of the X's that I have here. Our Y's is survive. Then we have to replace the conditions. So I'm going to do white, and I'm going to do green. And I have to update my iterations. I'm going to set it up for 10,000. And then I'm going to run. And you can see the stop sign is up, so it's running. It's just going to take a few seconds. So that is our first p-value. Now, how you do this is up to you. But I like to do it one at a time. So, our first comparison was made. This is white to green. Now I need white to blue. So I make a new chunk, copied and pasted, and what I did was copy and pasted this. We ran it once, we know it runs. Might not be correct, but it ran. So then I'm going to paste that in, and that means the only thing I have to change is this one color variable. So condition 1 was white, now we're moving to blue. Color blue. Gonna run it. And when that p-value pops out, I'm gonna write it down. And new chunk, paste, change white and green to white and red, and run it. So it's just copy and paste, updating it. Now I can put this all in one chunk. It is. Right, so I've got that. Copy and paste. All right, so we did all of the white comparisons. So now we've got green and blue versus green and red. So I'm going to go, already pasted this, so I've got green and blue. I'm going to run that, and while that's running, I'm just going to go ahead and highlight it and copy it. I'm going to wait for that to be done and save the p-value. That. Insert, paste. So this is green and red. And then I think the last one we have is blue. Yep, blue and red. Still running, still running. There it is. And now our last comparison is blue and red. This is our last comparison for the p-value. Got it. And this was white. What was it? White, green, blue, and red. White, green, blue, and red. Just keeping track of the order. All right, so save each p-value in a vector, and then adjust the p-values using Holm or Bonferroni adjustment. And that is up to you. So I have my p-value vector that I've created, and then p.adjust. We're going to adjust our p-val and method. I'll use home. And we know our comparisons, so I will go through here and what did I just go through? White and green is 0.53. White and blue is 0.083. And then white and red is 0.019. So white is not equal to red. White and blue are no different, so I know white and green are similar, and blue and green are similar, since their two extremes are not different. Well, I can go to the next, green and blue, that's similar. Green and red are similar. And all the other comparisons. I have to double check. I got my lines to appear appropriately on that on the exam 3 key. And I think I had to use an apostrophe or something like that. I had to use something. And that kept R from putting a line. So I have to look up what that was. That's our conclusion. So then our write-up, again, we report, let's see, write-up. We would do pairwise permutational T-test. And 10,000 iterations. With home adjustment, suggest that we have two groups in our data. White, green, and blue have similar survivals. And I would do p-adjust, p-ADJ, again, because we adjusted it. Those are all 0.05, and that would probably be 0.08. I take the smallest of those, which was 0.08. And then green, blue, and red flowers exhibit similar survivals. And again, p to adjust, or p-adjust, and I take the largest one, which is 0.89. I think that would be 0.89 would be sufficient. What if we ran all of the code in one chunk? I will show you what happens. So I'm going to go back to the white and green. That is our white and green. So I pasted the one time, updated it, I got white and green. I ran it once so I know it works. Then I copy it. And then I count how many. So we have 4 values. So we've got 1, 2, 3, 4, 5, 6 comparisons. So I'm going to paste it. So I got 1, 2, 3, 4, 5, 6. And I added a space between each of them just so I could keep track of it. And then I go through, I've got white and green, white and blue, white and red, and then I've got green and blue, green and red. Then we have blue and red. That's it. So I've got them all updated. I'm going to run it. And what it's going to do is run the script, or run each of these iterations one at a time until the entire chunk is done. So those individual chunks ran, what, 5 seconds, maybe 10 seconds at the most? I've got 6 of them in there, this could run up to a minute. All right. Now it gives you progress. Didn't always used to do that, but it at least gives us progress of where it's at. And what will happen is it gives all of our p-values down at the bottom. So we don't have to run it one time and then save the p-value. We have all of them there, so then I'm ready just to kind of save the p-values. And you can see that they're going to be different. Our small values aren't going to be different as much. But these can definitely, the larger they are, the more variance we're going to have. All right. So this gives a similar result, but the chunk takes longer to run because it has 6 pairwise permutation tests. This will also show a slowdown when knitting. All right, so to demonstrate this, I do have Word document. This is just going to be a generic Word document. So we're going to watch what happens when I knit it to Word. Processing file, and then it shows the chunk progress. Oops, line 199. Oh, hold on. I know what that is. We're going to have 2 errors in there. Where is our first permutation test? So this isn't going to knit for you. Here it is. This is the first one. Let me look up how not to run a chunk. R, markdown, don't run chunk. Maybe this. R eval equals false. Let's try that. So that works. That's our updated one. This one too. Let's try it. Processing chunk. There it is. All right, chunk 16. We hit 60%, and it's working. All right, it looks like it froze. I think this is the ANOVA. I don't think we hit the pairwise test yet. And then we hit chunk 20. These other ones didn't take so long. 21. Oh, these are the individual T-tests, pairwise T-tests. You see it adds however long it took. That's how long it's going to take to knit. All right, we're slowly going to get there. And it happens. But once we get to that one big chunk with all 6 of those things, it's going to look like it stopped and it's frozen. But it's still running. So is this going to happen on the exam? Guaranteed. Permutational ANOVAs are on this exam. They're at 98%. That's our last chunk. Chunk 27 is our last chunk to do. And that's going to be the one that takes a while. Yep, it should be. I think we're the only ones in here for the finals. Maybe a geography class.
Does the bio and magic class be here?
Well, it's scheduled. Let's see. 3101? No, that's I don't know.
The 4,000 class.
Bio 4420. Yeah, that's bioinformatics. Yeah, it's but is that a lab?
No,
That might be their lab.
I just know our lady doctor closed one day and she said I had teaching when I was at it. I said, cool.
All right, so it's knitted finally. Made it. We have 15 pages. It's got the output. We have our crucible test. All right, and that's cool. It shows the code, so eval equals false. That works. Add that so that way you can knit and it doesn't evaluate it. That's a cool trick. Got to remember that. Okay. Shows the output for that randomization. So how we wrote this, it still applied because the p-values were so low. And our post hoc tests, again, when we ran them, these are going to be different, slightly different. Yeah, that didn't work quite well. But you can see that they base it, we have the same conclusions. White, green, and blue formed a group, and then green, blue, and red formed a group. And everything works. So, just so you know, when you knit with these randomization tests, it's going to take some time. It will take some time. All right? Questions? All right, a practice data set is turkeys. That's CSV. So I'm going to import a data set. This is posted. There we go. I'm going to leave it at turkeys. I'm going to lowercase it. Strings as factors, import it. All right, so this is what we did. So assume I went to HEB last week, braved the crowds, which are crazy. I went to the frozen food section with all the turkeys and recorded the brand of turkey that was there and the weights that were in the bin. All right, and this is my data set. This is the data set, which, I mean, that could have been a honors project. It could have been an honors project. Wait for the turkey. There's hams out there. But we have the weights. All right, our question. So let's get down here. Let's get that in here. Yeah, well, that's it. Looking at the stuff that has the weight on it. All right, turkeys, CSV. All right, so in this, I recorded the brand of turkey and the weight listed on the tag. Are certain brands larger than do certain brands sell larger turkeys than other brands? All right, so what test do we want to run? What are the assumptions, and are those assumptions met? Run the appropriate test and post hoc test in order to answer the question above. All right, so that's going to be our practice for turkeys. I do want to point out, I've got the car library open, and we've been stressing the importance of our assumptions, and what happens when we violate the assumptions. I can create a QQ plot of our null distributions. Let's see if that's going to work. Distribution. See if that's going to work. How do I do this? QQ. Oh, hold on. It's lowercase. Degrees of freedom. What was our flower? I'm going to pull our degrees of freedom in another place. 3, 2, 5, 6. df1 equals 3. df2 equals 2, 5, 6.
So if it's normal,
You can still run permutational if it is unequal variances.
but it's not as strong, right? Or is it as strong?
It is just as good. Just once you go down the permutational route, you probably need to keep it that way. So our flower data said they were slightly non-normal. And if we looked at the null distribution, you can see that we're close to fall within our F distribution. So this is the QQ plot of the F distribution with the appropriate degrees of freedom. We're close to that. If we're close to that, then I'm going to guess that our T rand is going to be the same thing. So I don't know what our last one was run. Whatever one this was. T-Test. See what the output is. So I could do QQ plot of T rand. Distribution is a T, and DF is 1/15. There's a T distribution. So I did the QQ plot of our last comparison. This is blue versus red. And you can see that my T distribution, the randomized T distribution, does not follow the theoretical T distribution. And this is a great example as to why our randomization test would be much more powerful than running a regular T-test. And this was actually a Welch's T-test, but we're basically doing the same functions. All right, so go ahead and try turkeys. See what you get. And it's about, you have an error. Okay. All right, so what we'll do is we can pick this up on Wednesday. You can work on it. We'll review it on Wednesday. The idea is for you to go through it, and whatever you come up with, run a permutational test to make sure you're reviewing that and know how to do that. And then what I want you to do is, this is going to basically wrap up what we're doing. So I do have homework that's posted on ANOVA violating assumptions. So you can work on that, work through the final exam prep. I'm not collecting any of this final exam prep. This is the focus for Wednesday and Fridays to answer any of the questions. If you're working through it, say, I don't know how to do this, or I'm not sure the approach, bring that question to class. We'll look at this homework, we'll look at the exam prep, and we'll answer it, and we'll do it in class, as a class. All right? So you can take this time to work on those turkeys, or if you want to do the turkeys at home, you can. Is it?